My name is Professor Fawad Inam. I'm Professor of Mechanical Engineering and Head of Engineering and Construction Department here in the School of Architecture, Computing and Engineering at the University of East London. In this lab, our students carry out materials characterization, materials analysis activities. So for example, here we have X-ray diffractometer. In this equipment, students place their samples after they prepare it in this lab, and then they analyze the phases. So this is how they understand the phase composition of the material. So let's suppose if you get a new material, or if you want to understand what is in a particular product or the phases present in the material, this is the equipment they use. And behind me, we have XRF spectrometer. Again, the principle is exactly the same. The students use these facilities to prepare samples. We have grinding, we have polishing machine in this room, and then they place their sample in the XRF spectrometer. We bombard X-rays on the surface of the sample. They get diffracted from there, and that's how the detectors in this machine, they are able to catch those X-rays, those bombarded, those refracted X-rays, and then subsequently do the analysis in terms of the elemental composition and the phases that are in that particular material. And here we have scanning electron microscope provided by Joule. As the name suggests, we are using electrons instead of light to capture image, to understand about materials characterization, to understand about phases, to understand about the topography, to understand about what is inside that material. Our engineering students are using this microscope to understand about the factors, to understand about different types of aspects of the material, including the fractography, including the crystalline phases that are present in the material, including what is the cause of fracture that has taken place. In particularly for mechanical engineering, this is a key asset that our university have. If you look at your mobile camera, you can actually zoom in up to 10, 15, 20x. This particular equipment can go up to 250,000x. This is the power, this is the resolution of this scanning electron microscope. It can capture very sharp images using electron, and it is using some very sophisticated machinery like liquid nitrogen cooling chamber. It uses a high potential difference tungsten gun. It uses some very delicate, some very exciting technology that we equip our students with when it comes to their projects, when it comes to their research side of things, when it comes to their research assignments, when it comes to their PhDs, when it comes to their MSc project, including final year bachelor's projects. This is our general engineering flexible laboratory, we call it. Here we have our fatigue testing machine. As we understand, fatigue is about cyclic loading, about vibrations. So this is one of another key assets that we have in engineering. The principle is pretty straightforward. Our students, they machine these samples in our general engineering workshop, and once they achieve the correct geometry, they place it in this machine. It is connected to a computer which is capturing the data, and that's how they understand about the fatigue properties of materials. Here we have thick, slender equipment as well as thin, slender equipment, and we also have the creep testing machine. So for thick, slender and thin slenders, as the name suggests, our students practice what's going on with the hoop stresses, what's going on with the radial stresses within a pipeline or any cylindrical shapes. Obviously, if you think about oil and gas applications, if you think about chemical industry, if you think about general industrial practices, cylinders are always there, stresses and strains. So these equipment help our students to understand what's going on in those cylinders. We also have creep testing machine. Okay, so as we understand the creep phenomena, it's all about stress due to time, okay, material strain due to time in a constant stress. So the principle is exactly the same. We have connected digital connect with these equipment, so students can actually analyze the data, they can actually understand what's happening, they can plot the curves, and they can get a lot from their experimental efforts. In this section of General Engineering Laboratory, we have the universal material testing machine. supplied by Gunt. And we also have the Japanese hardness testing machine. So the principle for the universal material tester is pretty straightforward. Our students, supported by the technicians, prepare the dumbbell-shaped specimen, or depending on the mode of stress they are going to apply, depending on the mode of forces, they place the sample once they achieve correct geometry in this machine, and they apply forces. It can be in tension, it can be in compression, it can be torsion, that's twisting, or it could be 3-point or 4-point bending. They can also do the adhesion analysis. So let's suppose if they stick 2 layers of strips and they want to understand the strength of the bonding, that's what they can also analyze. As the name suggests, it's a universal material testing. They get the properties, they can actually use the computer to capture the data, or they can manually understand how the way it's calculating and how the forces are generating strain, and ultimately they can do manual calculation using this machine. Obviously, we get the key materials properties like elastic modulus, like ductility, brittleness, the area under the curve to analyze toughness of the material. And obviously that will enable them to understand about the fracture. Of course, if it's a brittle fracture, if it's a brittle material, it will be an instant or prompt fracture, and so on. Of course, on this side, we also have the hardness testing machine. At the moment, we have the Vickers indentation mechanism. So the principle is straightforward. With the help of technicians downstairs in the general engineering workshop, they achieve a mirror polished surface. We have the grinding machine, we have the polishing machine. Once they mount the sample in plastic, in a plastic casing, and obviously once it's fully polished, they let the machine to create a diamond indent. Okay, so the indenter drops very slowly and it produces an indent. And with the aid of this microscope, they capture the dimensions of the indent, and that's how they compute the hardness of the sample.
I am Ravindra Jaratna, Reader in Coastal Engineering at ACE. I teach EG 6114 Water Management in BSc Civils, EG 5031 Water Engineering in BEng Civils. On top of that, I supervise BSc, BEng, MSc projects as well as PhDs. So this particular open channel we use to demonstrate 2 different types of experiments. One is the sluice gate and hydraulic jump, where we take a number of flow depth measurements just before the gate, soon after the gate, just before the jump, and after the jump. And then by doing it, we will be able to calculate the velocities. Hence, we identify the different regimes of the flow. And on top of that, we have the broad-crested weir experiment, where we measure number of flow depth measurements, including the critical depth. Hence, we use the weir formula to calculate the discharge.
Hello, my name is Anka Chupala. I'm the module leader for the Level 4 Structure Mechanics EG 4015. We are here in one of the structures laboratories where the students need to carry out a number of experiments using the testing frames around us. Students need to work in groups to carry out experiments relating to the shear force in a simply supported beam, bending moment in a simply supported beam, deflections in a cantilever, and bending stresses in a T-shaped simply supported beam. For example, for the shear force, bending moment, and deflection experiments, students need to take the appropriate measurements for a number of load cases corresponding to masses varying between 100 grams and 500 grams, and to ultimately plot the corresponding diagrams. Then they need to calculate the theoretical shear forces, bending moments, and deflections for those beams, to plot those theoretical diagrams, and then to compare the experimental results with those theoretical ones, and eventually critically comment on the results. Similarly, for the bending stresses in the T-shaped beam, Students will need to carry out experiments and do theoretical calculations, which would include also the calculation of the position of the centroid for the T-shaped beam, the calculation of the second moment of area of that section, and the position of the neutral axis for that particular section. So ultimately, they would need to plot the theoretical and experimental stresses and strains diagrams across the section for that particular beam, and to compare the theoretical and experimental results obtained. Thank you.
Hi, my name is Saeed Afshin Javid, and Senior Engineer in Mechanical Engineering Department. Welcome to Advanced Manufacturing Workshop. My job is overseeing the engineering workshop activity here. At right side, and you can see the mill machine and lathe machine, which the student at first year, they use this general manual machine and will be competent in engineering discipline. Then in second year and third year, they move to use advanced manufacturing technology. That's called CNC HAS mini mill machine. They create something, they design something by using the software. It's called Fusion 360, the latest technology in design CAD/CAM. This is one of sample in here, a student they design. And from here, we provide PPE. We make sure a student they have relevant PPE before actually making any prototype. When we move to talk about prototype, as you can see in here, there are different designs, round shape in here, cubic in here, and any other design. As I explained already, this shape of manufacturing in here properly been designed by a student and then machine programmed and then manufactured with a high precision. That's the end of the route for any mechanical engineering student to be competent and be multi-skilled for future job. We have another set of art facility here. It's called Plasma Laser Cutter Westcott 84. We use this facility. First of all, we provide a relevant PPE for a student here, eye protection, head protection, and then if you look at this arm, it moves in X, Y, Z degrees, and it cut in different angle and different shape, as you can see in here.
My name is Thamo Sudarsan. I am the course leader for Aeronautical Engineering at the University of East London. This is our state-of-art computer simulation facility for flight design and flight simulation, where students can design their own flights, on aircraft according to the configuration. They can put their data into the computer there. Then they can simulate and see whether the flight can fly in the air. So you can see here we have the facility to simulate the motions. So that is the computer where you input the data, and this motion system adjusts according to flight pitch, yaw and bank and so on. So they can feel the real flight experience in the simulator. They can also use this simulator facility for research and other engineering fields, such as control design, where they can design PID controllers and things like that to control the control devices such as elevator, aileron, flap, and so on. So this will give a real experience for students to do some real engineering practice in the simulator. We can also use this facility for research, where we can collect massive amount of data according to the simulation. Then we can use different computer technology such as big data science or artificial intelligence to optimize the computer model for aircraft. So you can optimize the size of the wing, fuselage, and other control devices. And also we can use this data to optimize the control system to fly the aircraft in optimum, such as optimize energy consumption and so on.
Hi, my name is Samir Murad. I am a lecturer in mechanical engineering at the Department of Architecture, Computing and Engineering. Today, I am in the Mechanical Engineering Laboratory at UEL. Here, today, we have a centrifugal pump which allows the student to study and test on performances of a centrifugal pump and also the additional of effective turbines. The centrifugal pump, it's one of the most common machine that used in the variety of application to move fluid, including heating systems, appliances, agriculture and power. This makes centrifugal pump one of the most important and common machine in the world, and therefore a fundamental topic to teach fluid mechanics to future engineers. The system that we have here today allows students to learn about head and efficiency against flow. It displays the performances variables relating to inlet pressure and speed, and also flow measurements. This system have the ability to provide a extra 3 different turbines for advanced learning. Let's have a quick look around the machine. The centrifugal pump is connected to universal dynamometer, which powers the pump into that side, in which a separate turbine, including Pelton, propeller, and Francis turbine, can be fitted along with the turbine dynamometer. This allows students to do tests on the performances so they can understand how turbo machine works.
Welcome to the material testing lab. My name is Dr. Arunachalam Subramaniam. I'm a senior lecturer in mechanical engineering and I teach engineering materials at level 4 students. This is a tensile testing equipment with a capacity of 20 kilonewton. Tensile testing is a process, is a destructive method and experimental work to understand how materials behave when they are subjected to different kinds of stresses and load. Our students use this equipment to test different types of specimen and to understand the relationship between different types of materials and then corresponding deformations according to the various stresses acting on the specimen. The test is very simple. Specimens will be taken and then it will be clamped into these 2 collars, as you can see from here, and then a load will be applied uniformly until the fracture takes place. And this is the sample of the fractured specimens. And the corresponding behavior of the materials will be displayed over here. And then at the end of the test, graph like this will be produced, which is a load versus load against extensions graph. And students use this graph to calculate or to find out the relationship, to study the Poisson ratio, the ultimate tensile strength, and the elongations and other things. These are some of the specimens used in the experiment. This is, for example, is 0.5% carbon steel, and this specimen is aluminum alloy He15, and this is a sample specimen against use 70 by 30 brass. Thank you.
My name is Dr. Adnan Adnan. I'm senior lecturer at University of East London. Today, I'm going to provide useful information about softwares that could be very useful in the discipline of mechanical and civil engineering. I will start with SolidWorks. We have got 36 updated top-of-the-range machines over here in this room, which is KD226, and we got another 79 machines in KD228. I will like to start with the AutoCAD. The latest version of the AutoCAD are provided on these machines, which are updated and of high spec. Students can use 2D and 3D AutoCAD to practice and design their components to enhance their graphical communications. In addition to that, we have also provided latest version of the SolidWorks where students can construct their components in 3D shape, which they can assemble it as a family, one by one, or as a whole machine. In addition to AutoCAD and SolidWorks, student has also a facility of Revit, which is, I will say, is more like a building information management package, but there are some elements like plumbing, refrigeration, and air conditioning, and many more systems. What students can, mechanical and general engineering students can learn, and they can enhance their employability scope. Another useful system is the MATLAB, and it's been equipped with Simulink, where students from any field and can use it as a Simulink to simulate their experiment before they went into the field. For example, one of my recent students, he used Simulink to carry out the experiment on the solar panels, which was very useful. There are a couple of more packages which I would like to introduce. One is ANSYS Education Pack, which is like a simulation pack, and the other one is Virtual Gallery. I'm very impressed with the Virtual Gallery because before sending the students to carry or use the machines in the lab, they can use Virtual Gallery to carry out their physical experiments here so that they could not go through any of the hazardous accident. So with this one, I would like to thank you.
Hello, my name's Paul Nichols and I'm one of the technical associates that work here in the Digital Fabrication Labs at the University of East London. In these labs we like to encourage rapid prototyping, so that means we want to see an idea, maybe sketched out, and start making it as soon as possible, testing the concepts and trying out these ideas with quite simple materials. As we go through, we like to work up to more structural, more complex materials that might suit the application. So once we've tested out concepts with the laser cutters, we like to move on to 3D printing. So the workflow to get there is a little more complicated, but it's all, you've learned all the foundations with the laser cutting. And with the 3D printing, we can work at different scales and with a lot of different materials as well. Starting off, we have very simple bioplastics. It's very easy and quick and cheap to print with. The resolution of that is about 0.2 millimeters. And then as we progress an idea, we like to refine both the materials and the resolution. So in terms of materials, we can use specific resin-based materials that have specific engineering properties. And we also have a nylon printer that's very, very strong. And we can even add composite material to that, including Kevlar and carbon fiber. One of the most exciting machines that we have in our lab is the 6-axis robotic arm. With this, in terms of what it can do, it depends what you put on the end of it. So we have hot wire cutters, milling end effectors as well. And with the 6 axes, we have a lot more freedom of movement, which overcomes some of the limitations that we have with our other technologies, but we keep the benefits of digital fabrication. So in our space, because we're quite at the forefront of technology, there's always a lot of investment in this area, and we're constantly growing. So this year, in the new academic year, we'll have a fiber laser cutter. This opens us up to cutting metals right up to 17mm thickness, and also very, very high resolution. And we are also constantly investing in how students access the robotic arm and tools that can go on the end of the robotic arm as well.
Hi, I'm Daryl Brown. I'm a technician in the AVA building. We're currently in the casting workshop where we mostly work with plaster and make model making and castings from that. There's a few examples on here. We work with the architect students an awful lot. They make site models in a variety of different techniques for mold making. Often they would make it out of card, foam board, wood, because they're working with angled shapes, and then from that the mould would be this way round, and then if you pour the plaster in, saving a bit of plaster there, and then this is the result of their work, and that would be a waste mould, like a one-time deal. And then there's other techniques. So here we've got a 3-part mould that Mark has made. Mark is the other technician who's in this workshop, the main technician, and then from that they're making a set of cups. A set of cups that primarily Mark had turned on the wheel in the other room. And then further more to that, you can make a vinyl mould, and then a vinyl mould is something like this. So you've got a vinyl rubber inlay which recreates a release agent, so you can just keep making moulds over and over again. Yep, so that's a 2-part mould. They go together. And let me just run you through what this has happened here. So again, this is an object of Mark's. He's made a 2-part mould of that out of vinyl mould with a plaster shell to keep it steady. And then from that, he could cast it out of whatever, like plaster, resin, jesmonite. Take your pick really, anything that's not a hot metal. But he's made a wax version, and then with the wax version, he's then gone through the bronze casting process. And then using the furnace next door, which I'll show you in a second, he's then got his bronze result. And like I say, that's a process that you can adapt to kind of whatever form you want, but it's about being able to kind of keep doing it. Okay, as I was previously mentioning, Mark turned this wooden object, found object of his, well, technically it was his father's sculpture actually, into a bronze cast sculpture. So he did that. There's one stage missing, so he created the wax template which I mentioned earlier, which is like this. So this would be his object, and then he's created the runners and risers attached to his object, and then it's got a funnel top. And then from here they'd create a mould with a plaster mix, and then it goes into the kiln, it burns away all the wax, and then you're left with this plaster mould and your relief of your object, and the runner and risers are inside. And at that point, you would bring it over to here, to the bronze foundry. And this is a crucible where we would melt the bronze. We would have our casts in this sand pit. We heat the bronze to the temperature that it becomes molten. And then it's all quite automated, so it's very safe. You can control it here. It pours the bronze into your mould, and then we safely turn it off and move it. We used to have a far more archaic method, which maybe was a bit more fun, but far more dangerous, where we would manually grab the crucible out of the furnace and then tip it. But this is one we got a couple of years ago. It's a lot safer, and we can do multiples a lot quicker. Yeah, so once that process is achieved and the metal was cooled down, you would remove your mould by breaking it apart. It's a one-time thing, and you'd be left with an object a bit like this. So this is the bronze object. So these are the pieces that they're actually trying to achieve, and then these are all the runners and risers that I showed you earlier, and that's to allow the bronze to flow to your object. And then the artist or engineer, whoever was working on this, would then need to cut away all their runners and risers and polish up their finished bits to the standard that they want to achieve. And that pretty much is the bronze casting process, so how we go from an object like this to a bronze version of it. Hi, so now we're in the metal area of the workshop, where essentially we cut, bend, shape and attach metal together. Attachment process is different varieties of welding, so we have the TIG welder, MIG welder and then the spot welder. Spot welder is a very quick way that you can create forms with thin steel. The MIG welder is a bit more industrial, and then the TIG welder is somewhere in between. Yeah, so, and then a variety of hand tools for cutting metal and shaping metal. We have a guillotine for cutting sheet metal. We have a plasma cutter, and I'm happy to say we've got a new plasma cutter on the way and a new MIG welder on the way.
Hi everyone, I'm Dr. Jaswinder Lota. I'm a reader at the Department of Engineering and Construction, and I'm also the course leader for mechatronics as well as electronics and electrical engineering programs. Here we are today in the electronics store, which houses a number of electronic equipment for our students to undertake their labs for various programs. As you can see, we have a large amount of equipment here that ranges from a lot of state-of-the-art oscilloscopes. A few of them are kept there and all around the store. We also have a lot of power supplies and state-of-the-art network analyzers as well. And also there's a shelf there which has got all the discrete components that the students may need for their practicals or any projects that they may undertake, for example, resistors, diodes, and capacitors.
Hi, I'm Carl Lee. I'm the course leader for mechanical engineering, both the IMechE and the BEng. And this area is the general project area used by the students. Once they've been trained using the machinery, they're allowed to work in here to produce their devices or working on the Formula Shooting car in here, or on the IMechE Design Challenge Year 1 and Year 2 competitions.